Hi everyone and welcome to this lecture, and from today on we are going to see some examples of how we can solve a differential equation near its singular point, and we talked about the theory behind it in the past video. So let us start with an example, and we are considering an equation that looks like this: 2t square y double prime plus t square minus t plus, obviously there's a y prime there, sorry for that, and y equals to 0. And for t not equals to 0, let's say t is not equals to 0, and we can see that t times q by p, because this is just your p, this is your q, and r is just 1. R is just 1. So this will be just t into t square minus t divided by 2t, which is just 1/2 of t minus 1, right? And t square by rp is nothing but t square times 1 by p, which is just 2t, and this is just t. So if you recall that we said that t is equals to 0 is a singular point for p or something like that, and now you might be puzzled that I'm saying for t not equals to 0, but then I'm again saying considering t equals to 0. So that means that doesn't mean that it's contradictory in any way. What is happening is that the point of interest is always 0, but we are saying that the variable, it won't take the 0 value. That's been happening over here. So for t not equals to 0, we can oh yeah, I'm really sorry about that. I think I made a mistake. It should be 2t squared, yeah, not 2t, sorry. So this will just be 1/2. Okay, so as I was saying, that for t not equals to 0, we can see that these ratios times t is just polynomials, okay, and hence the power series occurring in our construction will converge for all real values of t. So that's why we can use the solution, that is the trial solution we saw in the previous lecture, into this differential equation that we wrote down. So if you recall that the solution was something like this: from n equals to 0 to infinity, there was this an and t to the power n plus r. And now what we're going to do, we are just going to differentiate it twice. So first, and this is similar to the example video that you saw when we tried to solve a differential equation near its ordinary point. So y double prime will just be n plus, oh sorry, yeah, there is a summation symbol right there, n plus r minus 1, a of n, which is just a constant number, and this will be n plus r minus 2, and y prime is just n equals to 0 to infinity. So this is simple differentiation. This is just n plus r, a of n, t to the power n plus r minus 1, like this. And now what you need to do, you just need to put these two things into this differential equation over here. So let's do that. If you do that, and obviously there is this t square term, right, and there is a t to the power n plus r minus 2. So you just put these things over there, and you just manipulate these powers. By manipulate, I mean just multiply them, or so to say simplify them. You will receive something like this. It will be pretty big, so follow me. That means hold your breath, or I don't know, just be patient. But the whole expression is quite big. So let me just write it down without any talking. Yeah, so this is the big expression that is coming from substituting these two guys into this differential equation. Now what we do, we just proceed like before that you saw in the early example video, that we want to extract out some factor of t, that means t to the power something, and here we have this n plus r thing, so we want to factor out t to the power n plus r. But to do that, we see that there are terms like this, t to the power n plus r plus 1, right? So we need to do something about this term over here, and again we will refer back to the method that we saw when we solved a differential equation for their ordinary point, is that what we're going to do, since we only want this n plus r, somehow we have to use some dummy variable to get rid of this, not get rid of this, but to convert this t to the power n plus r plus 1 into something like t to the power n plus r, right? Okay, and obviously we cannot make any change to r because r is not a dummy variable, but what we can do is that we can make a change to n, because n itself is a dummy variable. So what we're going to do is that now we're going to substitute m is equals to n plus 1 into the second term, and let's call this expression over here as 1. So we're going to substitute this, we're only going to write this because writing this whole expression every time is a really painful thing. So we're going to use this n and this 1, that is n plus 1, and we're going to rewrite this thing as m. So if you rewrite this thing, this will be, because this is saying you that n is equals to m minus 1, right? And you had n on the summation, so this will be just m minus 1 equals to 0. So that would mean m will just be starting from 1. So what people do is that they directly write it starts from m equals to 1. Also you can notice it by using this, that when n is 0, m equals to 1. So this will start from m equals to 1 to infinity. I am using n is equals to m minus 1, so instead of n, write m minus 1. So m plus r minus 1. So now I'm just substituting the value of n, that is this guy. So instead of a of n, you will have a of m minus 1, and finally you will have t to the power m plus r, right? But m itself is a dummy variable, is also a dummy variable. So to keep things consistent, we are going to now just replace m with n's. So this is the replacement part. So this second term will now look like this. However, now notice that this n is starting from 1, not equals to 0. So what we do now, this is just n plus r minus 1, a to the power n minus 1, t to the power n plus r, right? And now we are going to put this guy back into this big expression. So let me write that out fully again. Obviously I have to write a very big expression, but yeah, that's life. So I'm writing this again, but obviously please keep track of the summation, where it's starting, where it's stopping, because not all these summations will start from n equals to 0. As you can easily see that this is starting from n equals to 1. So let me write these things out. N plus r yeah, this is a summation symbol, don't get confused. It's just the handwriting is a bit bad. Oh, sorry, this is the second term, right? So yeah, I think I forgot the second term. Yeah, this was n plus r minus 1. Yeah, sorry about that. there should be a -1 like this, n plus r minus 1, and there was this a of n minus 1 t to the power n plus r. So a of n minus 1 t to the power, oops, I think there is no space. Okay, you know what, since I can factor out the t to the power n plus r, I'll just write it at the end of this expression, and I'll put a bracket on both sides. That will be more convenient, I think. So let me get rid of these things. Oops. So this is the coefficient of the second term, or so to say the summation over the coefficients. And finally the third term comes with a minus sign. Oh yes, and also sorry about this. This is not starting from n equals to 0. This is starting from n equals to 1. So this guy is starting from n equals to 0 to infinity, and there is this n plus r, a to the power, sorry, a underscore n, t to the, oh yeah, I decided to write t outside. So these are the problems with this series solutions. Like, it's very long, and sometimes it's very hard to keep track of the things, but let's be patient and try to do them step by step, and we should be good. Okay, so this is the final term that I'm writing. This is just an, and finally multiply with the t to the power n plus r equals to 0, right? So again, we demand that this t to the power n plus r is not equals to 0. This is the demand, because I already discussed it before. Because if t to the power n plus r or any of the t is 0, that's just a trivial solution. So we want the non-trivial solution. So what will happen is that since this is not 0, this thing over here is equals to 0. And now we have to find our recursion relation, right? This is now what we are going to do. To get rid of the summation, all the summation needs to be equal. That is, all of them has to start and end at the same point, right? But here we can see that this n equals to this, there is this n that starts from 1. So what we can do about it? There is a very tricky way to do go about this thing, is that what you need to do is that you see that there are these terms. Okay, let me just highlight it with another color. So these terms with that starts from n equals to 0, right? And after 0 there is 1. So what we can do, we can evaluate these sums for n equals to 0 and start these sums that is highlighted over here, and start these sums from n equals to 1, so that it matches with this term and we can take out the summation. So let me show you what do I mean by all this tricky stuff. So if you put n equals to 0 over here, that means for n equals to 0 you have evaluated this thing, and then the summation starts from n equals to 1. So let's do that for n equals to 0. So if you put n equals to 0 over here, you get an r, and there is a r minus 1, and there is a0, right? Obviously I don't know what is a0 is, or I'm not going to comment anything about it right now, but you will see that what I mean by this in a few seconds. So we are just evaluating for n equals to 0 everywhere that is possible. So the first term will be just 2 into r minus 1 a of 0, and then the summation symbol will be there, because this is just one term for n equals to 0, and this guy over here, it contains terms from 0 to infinity. So I have evaluated it for n equals to 0, so now it will start from n equals to 1 to infinity, and the rest is just the same, right? Okay, and the second term obviously starts from n equals to 1, so there is nothing to do about it. So leave it as it is, n plus r minus 1 a of n, right? Sorry, a of n minus 1. Yeah. That in the third term, again we need to evaluate for n equals to 0. So if you just put n equals to 0, this will give you r a0, r a0, right? And finally we'll have from n equals to 1 to infinity n plus r a of n, right? And then the last term, again put n equals to 0 and evaluate that term. So this is just a of 0, and you start from n equals to 1 to infinity, and there is just a of n, right? And this thing is equals to 0, and now all the summations start from and end at the same point. So after simplification, that is, just do one line of algebra, that is, you multiply r with r minus 1 and all that, and you bring the terms that comes with summation and don't come with summation together. You will have 2r square minus 3r plus 1 a0. Oh yes, yeah, this is the thing. So if you do that, this will come over here, and then it will have a plus, and there is n equals to 1 to infinity, and you'll have all these terms. Obviously I'm going to show you the simplified version. It takes a bit of algebra to go there, but the main trick is to equate to gather the coefficients of a of n and a of n minus 1. So all the coefficients you have for a of n, you just add them up, that's it, and that will be just n plus r minus 1 times, there's a third bracket, and 2n. So this is a huge algebra, and it's pretty simple, but it's lengthy. So that's just simplification that I'm doing over here right now. I'm just showing you the simplified result. A of n plus a of n minus 1 t to the power, oh sorry, there is no t, my mistake. And actually there is no need to write for this summation at all, because we already got rid of that t thing. So that's why obviously you can just ignore this summation symbol as well, but it's better to keep it and get rid of the symbol later. As long as you know what you are doing, you should be fine, but if you don't know what you're doing, just keep the symbol. So as I discussed in the theory video, that when we equate the lowest power of the t, obviously I got rid of t, but even if I had t, this would be just t to the power, the coefficient of t to the power r, because t was multiplied with this whole expression, remember, because this guy had a t to the power n plus r like this, and when you do this n equals to 0, there should be a t to the power r term like this over here, t to the power r, and this guy would have a t to the power n plus r, because that's what would happen. So this is the lowest power of t, and it's giving us a quadratic equation in r. And now we demand a not equals to 0. This is another demand. Why? Because if a is 0, then this part is just 0 itself, and since there is a summation, this is a summation thing, and all of this is equals to 0, that means all the individual terms will be 0. And there is another way to interpret it. In fact, that's the more proper way, because if you want a finite solution, your series must terminate somewhere. It cannot go on forever. In fact, this is the formal reason. That's why you say that this summation should end somewhere, because if you consider an infinite series, that doesn't make any sense. That's like a thing that is blowing up. Obviously there will be there will be many terms, but that is countable. Let's say it's a countable infinite, it's not an uncountable infinite. So that's why I to keep things simple, I just said to get rid of this summation we need to do this. So but the formal reason is your series should terminate somewhere. So that's the idea. Now we demand this a of a naught or a0 to be not 0. I mean a0 is not equals to 0, and this gives us, because we are considering this part will be 0 and this part will also be 0, and this part will give us the recursion relation, and this part will give us the roots. And we will only see example of the root when these roots are distinct, that is they are not equal to each other and they do not differ by an integer. So that's an example that I am discussing right now, and we'll see that there are 2 more cases and we'll discuss them in the next video. So now let's get on with it. We are demanding a naught is not equals to 0. That means we don't want the trivial part, so we want the roots, and we have to put this equation equals to 0. That means 2r square minus 3r plus 1 equals to 0. So let's do that. So roots, it will come from 2r square minus 3r plus 1, this thing equals to 0. And if you solve it, this is just what? This is just r minus 1, r minus 1 half equals to 0. Obviously you can do the algebra or use the quadratic solution. So this is r is equals to either 1 or r is equals to 1 half. So let's call this r2 and this is r1, and you can see these are distinct and they don't differ by a integer. They don't differ by an integer. And this is the case 1 that I talked that there will be 3 cases. So this is the case 1, and the other 2 cases will be discussed in the future. So obviously this is one part. Okay, so this is done, and equating this part, that is this guy over here, if you equate this to be 0, you have to make a demand that n plus r minus 1, this is not 0, because this multiplied with this, and this n is starting from 1. So if you take r to be any real number, positive number, it's never 0. That's what we have been doing, right? Because we don't want any negative powers of t. So that's why it's always greater than 0. So now we if you equate this guy to be 0 and you demand that n plus r minus 1 is not equals to 0, you will get a recursion relation Obviously I'm not doing the writing the whole thing. It will take like what, half an hour to write the whole thing properly. So I'll just show you the end result because it's rather simpler, and this is all coming from doing some lengthy algebra, that is multiplying 2 things, subtracting 2 things and all that. You can do that. So this is the recursion relation. Okay, and notice that it contains some r over here. This is where the role of r comes in. That's why we had to do all this algebra, all this t to the power r thing and all that, because there are 2 roots, right? One of them is r1, one of them is r2. So in reality this is not a single recursion relation. It in fact contains 2 recursion relations. One of them is for r1, one of them is for r2. So let's work with r1. Let's take r1 first. So this will be an minus a of n minus 1, 2n plus 2 r1 minus 1, right? But r1 was what? Only 1. So this will be now a of n minus 1, 2n plus 2 minus 1, that means plus 1. Now you know how to do this thing. If you try to evaluate some following terms, but remember this is starting from n equals to 1, not n equals to 0, because our summation got shifted to n equals to 1. So you have to start from n equals to 1 right now. So when n equals to 1, you will have a 1 here, and it will be equals to minus a of 0, 2 plus 1, that is 3. Then you will have n equals to 2, a2 will just be minus a1, right? And it will be 5. And if you put the value of a1, this will be plus a 3.5, something like this, right? So you can evaluate terms like this, and since we are considering for R1, our solution, if it is denoted one of the solutions, because there are two roots and there will be two solutions, because there are two recursion relations for that, and let's call this as y1, and this y1 will look something like t 1 minus 1 by 3t plus 1 by 15t squared minus 1 by 105. Obviously you have to calculate this term. There is no shortcut to it, there is no trick to it. This is a painful task. This is y1. Similar calculation, a similar calculation will follow for R2 equals to half. So instead of using R as 1, now you put half, so you now obtain a recursion relationship as a of n minus 1, there is a minus over here, to n, and there will be a plus 1 and a minus 1, so these two will cancel each other out, and this is another recursion relationship. So again, like before, if you evaluate it out and call the solution as y2, so this will be just t to the power half, because if you recall, why am I writing a t and a t to the power half? You might get confused, so let me clear it out for one last time. Because if you recall, sorry, let me just write it over here so that I don't have to scroll anymore. We wrote our solution like this, t to the power r summation over an tn, right, for n equals to 0 to infinity, and this part is coming from the recursions. But this guy over here, t to the power r, you have two r's, so for 2r you have 2y, that is one of them is y1, one of them is y2, and since at the first case we considered r as 1, that's why we wrote a t, and then we considered r is equals to 1/2, that's why we wrote a t to the power half. And again, from this recursion relationship you will get terms like 1 minus 1/2 of t plus 1 by 8 of, sorry, this will be t squared minus 1 by 48 t cube, and so on. And since it's a second order differential equation and we expect two solutions, and from the two recursion relationships we can obtain two y's, y of 1 and y of 2, and finally the general solution is just c1 y1 of t and c2 y2 of t, where this c1 and c2, they are just arbitrary constants that are determined from the initial or the boundary value problems. So the concept for solving this is very simple, but the actual task is pretty lengthy. As you can see, this is a pretty lengthy task, and in fact it doesn't matter how the roots are coming. All you need to do, you need to follow the steps like this, and it will work when the roots are real. And as I said before, we are not considering the complex number cases or the complex conjugate cases, and even though these two roots they do not differ by any integer, and you can see that this series, there is no nice function for it. You will see that when the roots repeat or the roots are different but they differ by an integer, there will be some common form of a solution. That's what we'll try to see through some examples in the next videos. So this will be it for today, and I'll see you guys in the next lecture. Thanks.